Hello everyone. So in this video we're going to talk about the columns that make up the periodic chart. In an earlier video we looked at how the rows were defined. And the rows were defined by the principal quantum number n, and when n is 1 we were filling the K shell moving left to right. When n is 2 we're filling the L shell. And when we get out here to the other side of the periodic chart, then these fellows over here, the noble gases, those represent these filled outer shells. And when those outer shells are filled, they don't bond very readily to other kinds of atoms, and we refer to those as the noble gases over here. But if you notice, we still have these big gaps that are somewhat still left unexplained from the previous video. We have this huge gap between hydrogen and helium. And then we've got this smaller but still significant gap as we go from beryllium to boron. And then that gap is now filled when we get down here. So what's going on with these columns and these rows in the periodic chart? Well, to understand that, we have to understand something about electron orbitals. So the electron shells, let's take a look at the Bohr model again. We've got a nucleus, and we have a K shell, and an L shell, and an M shell, etc. So this innermost K shell is both the smallest and it's at the lowest energy level. Now, because it's the smallest, it can only hold 2 electrons. And the first 2 electrons in any shell will go into what's called the s orbital. There's also a p, a d, and an f. And so these are the electron orbitals. And in this very nice diagram in the text by Klein and Dutrow, they show how the different shells, K, L, M, N, etc., can handle taking on different numbers of electrons and different orbitals. So for the K shell, remember the K is quantum numeral 1, so all we have is a 1s. So there's no other electrons besides just what can go into the first s orbital. But for the L shell, it's a little bit larger using this simplistic Bohr model. And in that model, with this larger shell, it can hold both an S and a P. Remember, the L is number 2, so we'll call that the 2S and the 2P. And that would distinguish, the 2S here would distinguish it from the 1S, the S orbital that is in this interior shell. Then the M, that M shell is greater still in size, and it can hold not just a 3S, remember this is the number 3 for the quantum number, not just a 3S, a 3P, but also a 3D. And then the N is larger still and can hold, the N is the number 4, 4s, p, d, and a 4f. So it's big enough to go all the way out to the f orbitals, and there are no other orbitals besides that. So as we get to these bigger and bigger orbitals, there are more and more electrons that can go in. So as we take a look at these orbitals, first we'll take a quick detour. This is figure 3-4, also in the Klein and Dutrow text from 07, they show the shapes of these. You'll find this in other chemistry textbooks too. So these are the s orbitals here. They have this somewhat spherical shape. These are the p orbitals there, and the d orbitals down here. Notice that this simplistic Bohr model where we have a nucleus and then radiating circles doesn't work when we get into filling in the p or the d orbitals. Now the elements have these very funny shapes. Now these shapes are actually things that are calculated. You might have heard of the idea that an electron can be a particle or a wave. Well, from the wave theory, there's some mathematics where you can calculate the probability that you'll find an electron somewhere. And what this shaded area is showing is that you have a very high probability of finding an electron in the p orbital, if one is in that orbital. You have a high probability of finding it here or here, but almost no probability of finding it out here. So they have these shapes, and there are times when understanding these shapes comes in handy and trying to understand how various kinds of atoms will bond together. But we just want to understand the structure of the periodic chart. So we'll just sum up here, looking back at the filling of the K, L, M, N, O, P, Q shells, etc. These first 2 columns represent the filling of the s orbitals. The s orbitals can only hold 2 electrons, so as we move left or right, once we fill in, an s electron here and another s electron here, that s orbital is full. Now the L shell is not full, but its s orbital is, so we would call these, this is quantum number 2, so we're filling in the first electron in the shell, the 2s1. This would be the 2s2. So there are 2 electrons in that 2s orbital. Then we would move on to filling the 2p. And there are 6 electrons that can go into that orbital before it's full. And when it is, then we're done with the L shell, and then we'd move on to the M shell. The M shell here, we'd fill in the 3s electrons, and then we'd fill in the 3p. Now, there is one strange thing that we'll have to deal with before we go. We're filling in the 3s, then the 3p. Back in the previous diagram, we said there's also a 3d. Where are the 3d electrons? Well, it ends up the 3d electrons are down here, situated in row 4. So let's fill out the rest of the quantum numbers here. So here we are in row 4. With row 4, we're filling in the 4s electrons. So the 4s electrons will go there. And we're going to fill in the 4p electrons here. But what's happening is that before we fill in the 3d, we're going to fill in those 4s. So the order of the electron filling is 3s, 3p, 4s, then 3d, and then back to 4p. Now that might sound kind of strange, but there's a very nice diagram, again in Klein-Dutro, that illustrates this. So here are the quantum numbers, 1 through 7. So the K shell, this is the 1s orbital. That's all that the K shell can hold, so there's nothing else to show here. We're plotting energy from low up to high. Here's the 2s at a higher energy level, so the 1s would always be filled before the 2s. Then we'd fill the 2p, then the 3s and the 3p. But take a look at this. This is where it gets tricky. Here is the 4s, and then here is the 3d. Notice that the 4s is at an energy level that is less than the 3d. So if we're going to add electrons into an atom and we're going to fill the lowest energy levels first, we're going to have to fill that 4s before we start on the 3d. After the 3d are filled, then we'll start on the 4p, and then after the 4p, we'll go after the 5s, but then we'll come back and fill the 4d, and then we'll come back and fill the 5p. So this is a stair step, and we're always going to go in order of the lowest energy first before we start filling something at a higher energy level. So that's really a big part of why we have these gaps here, and then this very odd ordering. And I guess we'll just finally end on this. Notice that we said at the end that we're filling in these orbitals. This should be a filled K shell, and this is a filled L shell. How about the M shell? Argon does not have a filled M shell. It's really kind of a colloquialism that we say that these things are full, because the M shell, again, that's quantum number 3, the 3D shell is not filled for argon. The 3D shell will only be filled after we reach the element potassium. And it's only when we reach the element krypton, well actually the element zinc, where the 3D electron orbitals would be filled. So what all of these have in common is not so much that their shells are filled, but that the p orbitals in any given shell are filled. So that's the electronic aspect that distinguishes the noble gases and makes them unreactive with other kinds of elements.